Okay, so we've been talking about here in chapter 12, we've been talking about kinetics. So remember when we sort of study kinetics, we're studying sort of how fast or slow a particular reaction will really take place. One thing that we sort of looked at the beginning here was something that's referred to as the rate expression. The rate expression basically allows you to figure out, how reactants are changing with time, how products are changing with time. As we talked about, because these are sort of one-way reactions heading from reactants to products, we would expect that as this reaction starts, that we should start using up a lot of our reactants. So we should see a decrease in the amount of reactants, while we should see an increase in the amount of products as they're being made over time. And what that means is we could do the rate is equal to the change in concentration of, say, the first reactant over time, and we would put a negative in that to indicate that it's decreasing with time. While if we went sort of to the product side, we would do the same sort of thing. The rate is equal to the change in concentration of the product over time, but that would be a positive sort of value as it is increasing with time. The other thing that was kind of important with that is you do need to take into account the stoichiometry that's involved. And as we talked about, you really can do it kind of two different ways. You could do it like a traditional sort of stoichiometry problem, kind of do the multiple relationship and then sort of do the kinetics part of it. Or you can sort of incorporate the stoichiometry into sort of kinetics calculation. And that's why we did on some of those, or a lot of those, 1 over the coefficient from the balanced equation. So when we did, like, say, the reactant, we would go the rate is equal to minus 1 over the coefficient of the reactant, change in concentration of reactant over change of time. That negative is also important, as we talked about, when you calculate something like the average rate. It does need to usually be a positive number. But if you're talking specifically about a reactant, you will actually end up with a negative number in terms of how it's changing. Or if you end up in the product side there, you'll end up with the product as a positive number. So the nice thing about sort of rate expressions is essentially, if you know basically just one piece of information, either the average rate for the reaction, if you know how one sort of species is changing with time, you can figure out pretty much how everybody else is changing with time. Any questions on those things we talked about, I think, last time? We also sort of finished up talking about some factors that affect the rate, things like concentration, things like temperature, and things like catalysts, which we'll talk more about here as we go through this chapter. But there are a number of things that, can have a either, I guess, positive effect on the rate, increasing it, or sort of a negative effect or decreasing it in that sense. So I believe this is sort of where we left off here. So we'll pick up here. This is the rate law. And the rate law expresses basically the relationship of the rate of reaction to the concentrations, really, of the reactants over a particular period of time here. Again, all my arrows are off. They all got moved somehow. So we'll just move my arrow there. So if we have this equation, this is what sort of the rate law looks like. And the rate is equal to K, which is our rate constant that we talked about earlier. The rate constant is sort of a constant value for a particular reaction based on how it's written and the temperature. It's a relationship that always, as the name implies, comes out sort of as a constant value for that. The concentration there is our concentration of our A for our reactant. That is obviously in molarity usually. This guy is also in molarity. X and Y, X are orders. So X is the order with respect to A. Y is the order with respect to B. And where do we get those values? Well, we do not get those values from the equation. So let me just rewrite this thing here. So sometimes people may think, well, I'll just take the coefficients there, and you actually don't. So those are found experimentally. So the orders are not the coefficient. They may end up being the same number, but they're not the coefficients from the balanced equation. So like X and Y. They're actually found experimentally. So what that means is typically in these type of problems, you'll be given some experimental type information, and you need to use that information basically to figure out, what are the orders of each of those things. You could also add up those orders. So you could add up X and Y together, and that'll give you the overall order for a particular reaction. The other important thing when we look at a rate law, which is different than sort of the rate expression that we've been dealing with, is if you look at the rate law, it is only the reactants involved. So only the reactants. So you typically do not see products in a rate law. It is just those reactants that are of concern. Again, they're kind of the starting material here to go to a product. They're the guys going to react. They're really the guys that are going to determine sort of how fast that reaction is going to take place. So that's also another thing. So we use rate expression like we did earlier to relate everybody in the reaction, but rate law will only deal with our reactants in this particular case. So how would we sort of use our information to figure out everything? Well, it's very common that you would be given like a table, for example. And you may be given a table of, hey, you did one experiment where the concentration of A was, say, 4 molar, I'm just making it up. Concentration of B was, say, 2 molar. And it may give you sort of an initial rate for that, where I move some stuff out of my way. There you go. Maybe got the rate here that is in molarity per seconds, maybe it's 6. Then they'll go, hey, you did this experiment again. This guy was 4 molar. This guy was 4 molar, and it was like 12. And maybe you did it a third time, this experiment where you had 2 molar and 2 molar, and this guy was like 3. We'll see how I did making up numbers here. So we could actually do this a couple different ways. If you sort of understand relationships of how concentration changes and rates change, you kind of look at the numbers and do it. I find that most people are not very good at that approach. So most people want to do some type of mathematical approach to do that. So the mathematical approach that you could do is sort of use this equation here, which is we could take the rate 2 divided by the rate 1 is equal to K times A to the X, B to the Y, divided by K, A to the X, and B to the Y. So we could use this sort of formula here to sort of figure out the orders and what's going on along with a table such as this. So when we see something like rate 2 and rate 1, it doesn't necessarily mean that you go to the table and you just take the first and second entry. You want to actually go to the table and you want to find basically 2 entries. Again, it doesn't matter. This table has 3. You could potentially come across a table that's got like, 4, 5, 6 entries in it. But you want to find basically 2 entries. And what you want to do is we're basically going to be doing some math here. So we basically want to make sure we don't have too many unknowns. So in order to do that, what we're looking for is 2 entries in the table where the concentrations of one reactant remains the same, while the concentrations of the other guy basically changes. So for example, if we actually do look here at entry number 1 and number 2, so if we looked at numbers 1 and 2, what we see is the concentration of A remains the same, while the concentration of B varies. And that's sort of what we're looking for. Again, we want one where something stays the same and something else basically will change. So what we're going to do is basically put that information into our equation there. And personally, from practice, if you go with the one that has the larger rate value, you typically will get kind of prettier numbers, nicer numbers in the end. You don't have to do it that way, but usually, when you look at the rate and you're comparing those two, if you kind of put the one with the larger numbers on top, you sometimes will get maybe a little bit more whole numbers when it's all said and done. Again, you don't necessarily have to do that, but it just kind of works out that way. So what I'm going to do then in this case is put everything from information number 2 in the table up on top. That means my rate is 12. K I do not know. I know the concentration of A is 4 in that case to the X. Concentration of B in that case is 4 to the Y. And now I'm going to put everything from entry number 1 on the bottom. And that means that my rate here is 6. K. My concentration of A is 4 in my made up example. Hopefully this will work out okay. And 2 here for this guy. So that's sort of the setup. Again, everything on the top came from the table from entry number 2. Everything on the bottom came from the table from entry number 1. Any questions on sort of that setup there? Okay. So what we could now do is really some math here to help us out. Well, if we take 12 divided by 6, that is 2. This K on top and the K on the bottom is the rate constant. And since it's a constant value, although we do not know what it is at this particular moment, we do know it should be the same number, which means this guy and this guy should cancel out as well. That's 4 to the X, 4 to the X on the bottom. Again, at this point, we do not know what X is, but X would be the same on top and bottom, which means although we don't know what it is at this particular point, those guys should also cancel out. 4 to the Y, 2 to the Y. When we do that, that ends up giving us something like 2 to the Y in this particular case, when you basically divide that out. At this point, we could solve for Y. You could probably see that Y is equal to 1 in this particular case. Now, you could probably figure that out by just looking at it. If you didn't or couldn't figure it out by looking at it, you could actually take the natural log of both sides, and that will work. So when you take the natural log of both sides, basically the Y will come down, and you're going to divide the natural log of 2 divided by the natural log of 2, which will equal 1. So that's mathematically another way you could kind of solve that if you can't just visually look at it and sort of figure out, sort of what the order would be. So what does that Y represent? Well, that Y would represent the order with respect to B. Once you've done that, the next thing that you would want to do is actually go back to your table. And in our case, since we kept A constant, we now would want to keep B constant and do the same thing, same type of calculation. So in my example here, we'll hope the second part will work as well. If I look at keeping B constant, it looks like entry number 1 would do that for me. And entry number 3 would do that for me. So what I would then go back and basically do the same thing for experiments 1 and 3. Again, looking at my sort of rate value, I see that number 1 is a larger value for the rate. So what that means is I'm going to put all the information for number 1 up on top in my made up example here. That means up there, my rate is 6 is equal to the concentration, okay, times the concentration of A in number 1, which is 4 to the X, and my B, which is 2 to the Y. And again, all that information comes from entry number 1 in the table. Entry number 3 in the table then would go on the bottom there. So we got 3 for the rate. Okay. My 2 there. And my 2 to the Y. So at this point, we would do a similar type of calculation. We would do that. That's going to give me 2. Same reasoning here. K and K will cancel because don't know what it is, but should be the same number. When I do the 4 to the x divided by 2 to the x, that leaves me 2 to the x. And those guys will cancel out because they are the same. Again, you could do the same thing, natural log of both sides, or you can probably, in this case, just visualize that x is equal to 1. 2 to the 1 is 2. And that would be the order with respect to A. Any questions on that there so far? Okay, so now that we have the order for A and the order for B in our made-up example here, we could actually write the completed rate law at this point for this made-up example. And that means that the rate law would be the rate is equal to K times A to the 1 and B to the 1. Just like most things in chemistry, because it's to the 1, you don't have to put the 1s up here. So most of the time, people don't put the 1s up there, again, because it's 1. If it was some other number like 2 or something like that, obviously you would put it. But again, usually they will leave it off because it is 1, like most things here in chemistry. That means that the overall order for this reaction can be found by simply taking the values of x and y together. And if we do that, then we will end up with the overall order of the reaction is 1 for x and 1 for y, which means this reaction is what is referred to as being second order. And we'll talk about that a little bit later on as well, what that sort of means in this particular case. Any questions on that so far? Now that I've got me the completed rate law with the orders, I've figured out the overall order is second order for the reaction. At this point, once I do all those steps, I now can actually use my rate law and I can actually come up with what is the value of K. So we can actually use this information to figure out the actual numerical value of K at this point. We would rearrange our rate law and solve for K. So K in our case would equal the rate divided by the concentration of A to the first power and the concentration of B to the first power. So your question is, like, where would I maybe get those numbers from? You would actually get those numbers from the table. You could choose the first entry and do it. You could choose the second entry and do it. You could choose the third entry and do it. It doesn't really matter as long as you keep all the information from, obviously, the same entry. So for me, I'll just, in my example here, do the first entry. So in my first entry, it is 6 molar seconds as the rate. The concentration of A is 4 molar, and the concentration of B is 2 molar in this particular case. So basically, in this made-up number, 6 divided by 4 divided by 2 gets us something like 0.75. Now, in terms of units, molarity up on top cancels molarity on the bottom. We still have a molarity on the bottom. We actually end up with 1 over molar seconds as the units associated with the rate constant are m to the minus 1, s to the minus 1 is another way you could write that. These units for the rate constant, as we will talk about, are really important because actually just from the units that you see associated with the rate constant, you would actually know it is second order. So those are very common units for second order reactions to have that 1 over molar seconds. Any questions on sort of where all the numbers came from, why we did any of those things? So this is a typical sort of approach that you want to take to these sort of kinetics problems where you're trying to determine what is the rate law. You, again, will typically be given a table, and you kind of need to kind of do that approach is usually the right way to sort of do that. All right, so why don't you try one here, take a couple minutes, and why don't you figure out the rate law? If I grab my pen, there we go. Figure out the rate law, the completed rate law with the orders. Also figure out the value of the rate constant based on this reaction and this table that comes from the experiment. With our orders, we can start with sort of the generic rate law here, which would be the rate is equal to K in this case, F2 to the X and ClO2 to the Y. Again here, just the reactants involved. Also, we do not use, obviously, our coefficients here as our exponents. That's really why we do have this table sort of given to us. So we want to look at keeping one of the reactants, in this case, constant, while varying the other. So again, if we just kind of look at numbers 1 and number 2, that would do it for us, because that will keep our F2 constant while we are varying, obviously, our ClO2. So we'll go with experiments 1 and 2 here. Again, I'm going to go with the larger value for the rate on top. And again, you don't necessarily have to do it that way. It just will give you a lot of times a nicer whole number to sort of do it that way. 0.1 to the X and 0.04 to the Y. Again, all that information I just wrote came from the second entry in the table. We're going to divide it then by everybody's information there in number 1's entry, 1.2 times 10 to the minus 3, K, 0.10 to the X, and 0.01 to the Y in this case. We do a little division there. That's going to give us 4, I believe. So that should give us 4 is equal to, again, don't know what K is, but should be the same number, which means obviously it should cancel out. Don't know what X is up on top, but again, should be the same number up on top and the bottom. So those guys will completely cancel out to 1. And when we do our last division there with the Y, we will end up with 4 to the Y. Again, you can take the natural log of both sides and divide it, or just be able to probably visualize this one, that Y is equal to 1 in this case. Any questions on that part of the calculation?
Professor, yes, I
Yeah.
just sent a chat, but I'll just say it.
Yeah.
So I flipped those and I still got, y equals 1.
Yeah.
Is that okay too?
Yeah, no, it's perfectly fine. It's perfectly fine. You could put either one on top or the bottom. Again, what I was
Okay.
saying is, if you choose the one that is has a larger rate, you'll oftentimes get an answer where you look at it and it's like, okay, I could just see it's 1, more like
Right.
whole numbers. When
Mine
you
was
flip it,
decimal.
yeah, exactly. When you flip it, you get the decimal. Not a problem. It'll come out the same. You might not be able to maybe visualize a lot of those answers. You may need to do the natural log of both sides and divide it, but it should come out exactly the same. So you don't have to always do that one on top, the larger one. But I just say that because, again, sometimes it just gives you a little bit more whole numbers than decimals, but it should come out.
Yeah,
Yep.
that makes sense. Thank you.
You're welcome. Other questions on that? Okay, so now that we have got our Y, what we want to do is again go back to the table, and since we kept F2 constant last time, we want to keep the ClO2 constant this time. And it looks like entry number 1 will do that for us, and entry number 3 will do that for us. That keeps those guys sort of constant. So we'll look at those two experiments 1 and 3. And again, like the question was just asked, you don't necessarily have to do it this way, but you can put whichever one on top or bottom you like. But again, I'm going to go with that kind of larger rate value up on top. So I'm going to put everything for number 3 up there on the top. So that's going to be 2.4 times 10 to the minus 3 is equal to our K and our X, which is 0.2 to the X, and our Y, which is our 0.1. And now I'm going to put everything from entry number 1 up there on the bottom, or down there on the bottom, I guess would be the better way of saying that. Gets us that, and we'll pop that guy in, and we'll pop this guy in. Okay, So when we do this, again, we're going to end up with a 2, same approach here. K should be the same because it is a rate constant. When we do this division here, we are going to get that 2 to the x. This guy obviously would cancel out to 1, and that is going to give us x is equal to 1 in this case. And that would be the order with respect to F2 in this particular case. Now, won't always be ones. This example is there are obviously other numbers you get to zeros, and things like that. But what that means is now that we have the orders, we can write the actual completed rate law, which would look something like the rate is equal to K times F2 to the first power, ClO2 to the first power. Again, we don't have to put the ones there because it's assumed to be 1 in that particular case. We also know now that the overall order of this reaction is 1 for X and 1 for Y, which again means that this particular one is also a second order reaction here. Once we have our rate law, we then can use our rate law and the information in the table to actually solve for the value of K here. And to do that, what we'd want to do is rearrange this like we did on the previous one and solve for K. So we're going to divide everybody to the other side to do that. That's going to give us the rate divided by F2 and ClO2. And again here, you could choose whichever entry you like to do that. The only thing obviously is you can't mix and match. So if you choose entry number 1, you need to use all the numbers from number 1 or number 2 or number 3, whatever it may be. So again, I'm just going to go with the first one there and put it in 1.2 times 10 to the minus 3 molar seconds divided by our 0.1. Whoops, put the M, and our 0.01 with our M. And if we do that there, we will end up with 1.2 to the minus 3 divided by 0.1 divided by 0.01 gives us a rate constant of 1.2 units. Again, molarity on top, and one of the molarities on the bottom will cancel. 1 over molar seconds would be the units associated with that. Any questions on any of those steps, where we got any of the numbers from, why we did any of those things? All right, so some people may be asking, like, okay, that's nice. What does really all that mean, right? So what does all this mean? Who knows really, but we'll talk about it maybe. So let's just take this rate law. What does it mean, like it's first order, or it's first order here? What does that mean? What does that affect? So let's just say, for example, I'll just use kind of different numbers here. Let's say that we started out with a concentration of F2 equal to 2 molar, and we had a concentration of ClO2 that was 2 molar. And if we use our rate law here, and just to keep the numbers pretty simple and straightforward, I'm going to say our rate constant in this case is actually just 1. I'm just going to keep it as 1, whatever it was, 1 over molar seconds, right? So just keep the numbers pretty easy. So if I wanted to figure out what my rate was, right, I know this would obviously be 1, and in my made up example, this would be 2 molar, and this would be 2 molar, which means what would end up happening is I would end up with a rate of 4 molar seconds, right? In this sort of made up example. So how does sort of one reactant affect the other reactant? Because in this case, they're both first order with respect to each other. Let's just say that we kept in another experiment the F2 concentration the same, but we decided, hey, let's double the amount of ClO2 we throw in there. So let's throw in there 4 molar, right? So if we went back into our rate law here, again, using our same sort of values for the K and 2 for our F2, but here we actually double the concentration of our second reactant in this case, what we see in terms of the rate is the rate now goes from 4 molar to 8 molar per second. It doubled, right? So the rate from here to here doubled. When we doubled, basically, right, the concentration of the other reactant. So when we think about orders and we think about sort of what does it mean, it's sort of like the proportion of these things that you need to put together to achieve a certain rate. And depending on what their individual orders are, by changing one or the other, you can really affect the rate. So for example, if we had this same one here where, let's just say the rate law that we came up with was that the rate is equal to K F2 and ClO2 squared, let's just say, for example, right? Obviously, it's not in this case, but we'll just say that we came up with this one was our rate law. And we did sort of the same approach here that we were just talking about. By having a second order for Cl2, let's see what happens to the rate in terms of that. So we'll put in our information from our first value there, and we would have 2 molar here. This guy would be 2 molar squared, right? As you would need to have the 2 there. That's going to give you a rate to open up with as 8 molar seconds. Now when we double that second guy, let's see what happens. The rate would equal, again, just using that simple number of 1 for our rate constant, 2 molar, and now we have 4 molar squared. Now 4 squared is 16, I hope still, times 2 gives us 32 molar seconds as the rate. So in this case, we went from 32, or from 8 to 32, which is a 4-fold increase, right? 4 times, right? By just doubling it in this case. So in this case, doubling it caused the rate to go up by 4-fold. And that's because the order here, the rate is really affected more in this case, right? Because the order here was 2 in this made up example. So that's sort of what these sort of orders mean and these rate laws mean. It allows you a way to sort of think about how they interact with each other. And again, by adjusting concentrations, you could obviously play with the rate. Any questions on that? Okay. So the other important thing that we've sort of been talking about in terms of these are, again, that's pretty far off, that the rate laws are always found experimentally. So we always find these guys experimentally. They are always in terms of the reactants, not the products. And the order is not the coefficient, which is what this is trying to show you here. It kind of missed the circle. I was trying to circle that one, and the 1 was here. Sorry, some of these things got adjusted weird. But again, as we see here, ClO2's coefficient is 2, but the actual order that we determined was 1. Any questions on that? Okay. All right, so take a second here. Why don't you do this one? The rate equation for the following. If the rate is 6.6 times 10 to the minus 5 molar seconds, when NO is 1 times 10 to the minus 6, and O3 is 3 times 10 to the minus 6, calculate the rate constant. Here, they actually gave us the rate laws, so that's a nice, easy first step there. So obviously, they gave us that the rate is equal to K times NO03. And they gave us the actual rates there and each of these concentrations, which means, again, we just need to rearrange, dividing everybody to the other side, and basically plug into here our values. So that would be 6.6 times 10 to the minus 5 molar seconds divided by our NO concentration. which looks like 1 times 10 to the minus 6 molar, and our O3 concentration, which looks like 3 times 10 to the minus 6 molar in this case. That means we'll do some calculations there, and it looks like we do end up with, again, you want to make sure you use your exponent buttons here, obviously, like we talked about earlier. We'll go with 2.20 times 10 to the 7, if I counted decimals right there. Units, again, top molarity, one of the bottom molarities will cancel. That's going to leave us our 1 over molar seconds, or again, m to the minus 1, s to the minus 1 is another way you could write that. And that does make sense in terms of units. That's actually what we see with our second order here overall, again, because NO is 1 and O3 is 1 in terms of its order, which gives us that second order. Question on that calculation there. And again, just a note on that, as we saw in that sort of example I did, it was a 1-to-1 relationship basically in terms of those orders. So as we saw in that example I did on the previous page, when we doubled the concentration, the rate doubled, as opposed to when it was like a 1-to-2 relationship in that example there on the previous slide, wherever I did it. There it is. Oops. When it was, come here, over here, when it was a 1-to-2 relationship, basically in terms of the orders, as we doubled the concentration, 2 times 2 is 4, right? The rate went up by 4. So again, that's sort of what the orders sort of tell us, is that relationship of one reactant to the other. Any questions on that? Okay. All right, so why don't we give this one a go here? We'll throw that arrow. I have to fix these slides. Everything got moved, especially with the arrows. All right, so we have this one here. What do we want to do on this? We want to determine the rate law with the orders. We also want the value of the rate constant. So why don't you take a few minutes here and see what you come up with based on these numbers. And I think this is the one that's in your notes. I think I changed it, but just not. Make sure what you're seeing on the screen is actually what's in your notes. So use the values that you see on the screen. All right, so let's take a look here and see how we're progressing. So again, we want to take the same approach. Remember, we really can't determine sort of the orders here just from the actual equation. If we did from our equation, we would assume it would be 1 and 3, and it probably will not be 1 and 3. So what we need to do, obviously, is use this table like we've been talking about. We could start with sort of the generic rate law here. So the rate, again, would be K, just our reactants involved here to the X, and our I minus to the Y. Approaching the table here, again, we're looking to find two entries where one of the concentrations remains the same and the other one is varied. So just looking at it here, we see right off the bat 1 and 2. We'll keep our S2O8 2 minus constant while varying our other. So that's where we'll start with. So we'll look at 1 and 2 here. Again, for me, I'm just going to go with sort of the larger sort of rate up on top just to get a little bit more whole numbers. So I'm putting everything from experiment 1 up on top. And then I'll come back and put everybody from experiment number 2 on the bottom. Any questions on that setup there? All right, then we'll do our math here. So taking that, that's going to give us a 2. Same sort of theory here. Don't know what K is at this point, but we do know it's a constant value, which means it should definitely be the same. We don't know what X is at this point, but it should be the same on top and bottom, which means those guys should completely cancel. And here, if we divide these guys out, that looks like perhaps a 2 to the Y in this particular case. Again, here, if you can't visualize it, you can take the natural log of both sides and divide. And when I say what I mean by that is you take the natural log of 2 and divide it by the natural log of 2 in this case, which would equal 1. So the order with respect to I minus we just found was 1. Any questions up to there? All right, then going back to our table, since we kept the first guy constant, we want to then keep the second one constant. And it looks like we could achieve that by going with number 2 and number 3 here to keep that one constant. So looking at 2 and 3, I, again, for my personal preference, going to take the larger rate there up on top. And again, putting all the information for number 3 in. And then all the information for number 2 would go on the bottom here. All right, so we do a little math here. That's going to give us a 4 is equal to, again, not sure what K is. When we divide these guys here, we get 2 to the X, and these guys would cancel. Again, you could probably just visually see it here since we have nice, clean, whole numbers. But again, if you cannot visualize it, you can do the natural log of both sides. So what you would do is take the natural log of 4, hit equals, divided by the natural log of 2, and you will see you will end up with a 2 in terms of the order with respect to the S2O82 minus. Any questions on that there? That means now that we have our orders, we could write the completed rate law, which should be the rate is equal to K, and that is S2O82 minus, and the order was squared in that case, times the concentration of I minus, which the order was 1. This would be our completed rate law. With our overall order for this reaction, actually in this case being 2 plus 1, which means this would be third order type reaction. And the last thing that we could do now that we have the orders for everybody is we could go back to our table. We could choose any entry we want. Again, I'll choose the first one. And we could actually solve for K. So K in this case, dividing everything on the right-hand side to the other side would equal the rate divided by the S2O82 minus, and you still need to square it, times the I minus. So putting in our values there from the first entry, that gives us 2.2 times 10 to the minus 4 molar seconds, divided by our 0.08 molarity, again squaring it, and our 0.034 molar here. And if we do all that good stuff there, 2.2 to the minus 4 divided by 0.08 squared divided by 0.034 gets us a 1.01 as our rate constant for this particular case, I believe. 1.01 units. 1 molarity will cancel, 1 molarity cancel, still have squared molarity on the bottom actually, and something like this. Any questions on any of those steps where any of the numbers came from? Any questions on that? So here again, you can see not always going to be ones for everybody. You know, you can obviously have some other numbers. Any questions? Okay, if there's no questions, then let us try one more here. Let's do the same thing. Let's find the rate law with the orders. Let's find the value of the rate constant based on this table here. Okay, so let's see how we're doing on this particular one here. So we want to approach it the same way. So our rate here would be K times our reactants, our NO2, and our CO to the X and to the Y in that particular case. In this particular case, we actually have a table with more than 3 entries, which is possible. Like I said, you could have a giant table of entries, but really you just want to approach it the same way. So we're looking to keep one of the concentrations constant and the other one varied. By the way, as well, not too commonly seen, but sometimes you could even have 3 reactants as well. So you might even have 3 values on the reactant side. In those cases, you would want to keep 2 of the concentrations constant while varying the other. So the goal here is to just really have sort of one unknown. So it is potentially possible you could have, maybe 3 reactants, probably not more than that, I would think. And that's probably pretty rare, probably 3 of them. But you just approach the same way, keep 2 of them constant while varying the other. So in this case, actually, if we go with 1 and 2, that will achieve the CO remaining constant. So let's go with that first. Why not? We'll go with number 1 here and 2. And again, I'm going to go with the larger rate on top. So that's number 2 for me. And that means up on top would go 0.0082 is equal to K. And again, all the information there, we have 0.2 to the X and 0.1 to the Y. Coming back through and putting all the information in number 1 down there, 0.0021 K, our 0.1 to the X, and our 0.1 to the Y. All right, so we do a little division there, 0.0082 divided by 0.0021. That gives us something like, we'll call it 3.905, we'll call it. This is going to cancel. When we do this guy here, that's going to give us 2 to the X. And over here, these guys, again, will basically cancel out from each other. And roughly, that's probably about 4. But again, here, if we do the natural log of both sides, so if I take the natural log of 3.905 is equal to the natural log of 2 to the X, we end up with the natural log of the answer there divided by the natural log of 2. And again, when we do this guy, we end up with the X will come down. X is equal to, in my case, 1.97, which is pretty close to 2. So we could round in this case to 2 in this particular case. Any questions on that? Could probably just roughly probably round it to 4 here, and then you would see 2 to the 2 would equal 4. All right. At that point, we then could go back and to our table and keep our NO2 constant. And it looks like our only option to do that is number 2 and number 3. We'll keep that guy constant. So 2 and 3. And again, here, I'm going to go with this guy's just slightly larger, I guess. We'll go with number 3 up on top. So that's 0.0083 is equal to K and 0.2 to the X and 0.2 to the Y. While on the bottom, we'll go entry number 2, 0.0082 K, 0.2 to the X, and 0.1 there to the Y. Doing our division there, pretty much going to be 1. You get something like 1.01, if you will. Is equal to those guys that cancel out. These guys will also cancel. These guys will give us basically 2 to the y in this particular case. Basically, this is the natural log of 1, right? Which is basically 0. So this actually would be 0 in this particular case. So even though it's a little bit off, you could probably round it to 1. You take anything to 1, that will give you y is equal to 0 in this particular case. Or if you really do the math, 0.02, which is essentially 0, basically, if you do the natural log of both sides. So you can do a little rounding here to 1. And again, anything to the 0 power equals 1. So the order with respect to y in this particular case would be 0. Question on that there. At this point, what that means is our actual rate law in this case would be the rate is equal to K times NO2 squared. Because this is to the 0 order, we typically wouldn't put it in because that would equal 1. So this would really be sort of our completed rate law. We don't typically put it in like that, again, because that basically equals 1 in that particular case. That means the overall order here would be 2 plus 0, which is second order. And that leaves us really, that basically leaves us just K to solve for. So K in this case would equal our rate divided by NO2. Again, we want to make sure we square it. And you could choose any entry. So again, I'll just go for the first one. So 0.0021 molar seconds. Our NO2 is 0.1 squared molarity. And that will end up with there you go, 0.0021. Looks like 0.21, and that would be units of a molarity up on top, and one of the molarities will cancel 1 over molar seconds. Any questions on that? So you may say to yourself, well, all right, so just to sort of explain to you what these orders really mean. Technically, if we look at our rate law here, our rate is equal to K NO2 squared, and I'll put it in the CO to the 0. So what will these sort of orders and how will they affect the sort of the rate of the reaction? Yeah, so for the most part, the orders usually will be a whole number. So especially in something like that, like for example, the bottom one, we had 1.01. It's probably okay to round to 1, and like well, it's the top one there was like almost 4, I think, right? 3.9 or something like that, or 1.9. So you usually can round pretty close to it. And then if you do the natural log of both sides and get sort of a decimal, you can probably round usually to the nearest whole number is usually pretty good. Other questions on that? Okay, so just again to demonstrate sort of what those orders mean in relationship to sort of what's going on in the reaction and the rate of the reaction. Let's again, just to keep the numbers simple, let's say we had a rate of 1, whatever the units there is, 1 over molar second squared. And let's say we started with a concentration of NO2 as 2 molar, and again, our CO as 2 molar. So if we put it into this rate law using those numbers, 1 over molar seconds times our N2, which is 2 molar squared, times our 2 molar to the 0. Again, this is going to be 0, which means we will end up with a rate of 4 molar seconds in that case. So what happens then if I double my CO, just like I talked about in the previous one here? If I double the CO, well, if I double the CO, my NO2 would still be 2. This would actually still be 1. Get my eraser there. There we go. Put in the actual number, 1 over molar seconds. This guy would still be 2 molar squared, and this guy would be 4 molar to the 0. Still going to basically be 1, which means my rate would be 4 molar seconds. So in this particular reaction, if we for some reason chose to double the CO, quadruple the CO amount, we're not going to see a change in the rate at all, because the concentration of the CO really has no effect on the rate. And that's what we kind of see here. In order to affect the rate, we would actually need to change the concentration of this guy. So if we change that guy's concentration from 2 molar to 4 molar and kept the CO at 2 molar, what we would see in that particular case is we would have the rate is equal to 1 over molar seconds. And now that is 4 molar squared. And again, this guy is 0. This is still going to 0, but by doubling our concentration of NO2, we now will end up with a rate of 16 molar seconds. So we can see in this particular case, by doubling actually the NO2, our rate goes up by a factor of 4 in this particular case. So again, this is what those orders sort of allow you to understand, which reactants are important in the overall rate of the reaction, which ones may not be. In this particular example, the CO, because of its order of 0, basically you can do anything you want to it, it will have no effect on the rate. Any questions on that? And again, obviously just using very simple numbers to hopefully demonstrate that. All right. One last one here to finish up this sort of talk here about figuring out orders. Let's do the same thing. We're looking for the rate law and the value of the rate constant as well. Our NO2 minus. So looking at the table again, we got 4 entries. So let's see here. Looks like this guy and this guy will keep these guys the same. So we'll go with 3 and 4 as the choice I chose. And go with number 4 up on top. That's going to be 21.6 times 10 to the minus 7 equals, and by the way, don't forget the times 10 to the minus 7 that's here in the actual table. That's going to be our K times our 0.2 to the X and our 0.0404 to the Y. If you forgot the times 10 to the minus 7, you may actually be okay in this part of the calculation. 10.8 times 10 to the minus 7, our K, and our 0.2 to the X, and our 0.0202 to the Y. That I believe is 2 is equal 2 to the Y. So Y here would equal 1 in this particular case. Any questions on that one? And coming back to our table now, maybe 1 and 2 will stay constant. So looking at 1 and 2 here, I'm going to take 2 up on top, which is 32.3 times 10 to the minus 7. Our K, 0.06 to the X, 0.2 to the Y. And then our 2, our number 1 there on the bottom, 10.8 times 10 to the minus 7, K, 0.02, and 0.2. That should also give me maybe a 2 in that case, 2.99 maybe. Whoa, come here. There we go. 32.3 to the minus 7 divided by 10.8 to the minus 7. That's going to give me 2.999. That's roughly 3 in that particular case, give or take. And these guys will cancel. These guys will give me a 3 to the x. And those guys will completely cancel. And roughly here, x should be 1. That means that our completed rate law here would be the rate is equal to K times concentration of NH4 to the first and NO2 also to the first order. The overall order for this reaction would be 1 plus 1, which equals 2, our second order. And to solve for K in this case, we will rearrange and come up with our NH4 plus and our NO2 minus. Again, we could put any entry we want in there. This is where you will get the wrong answer if you've ignored that to the -7. Over here, you'll be okay because these guys will cancel. But if you ignore it here, you obviously will get the wrong answer. So make sure that you did not ignore it, hopefully. 0.02 molar and 0.2 molar. That's going to get us -7.02 divided by 0.2. And that is going to be 2.7 to the -4, 1 over molar seconds as our relationship here. Any question on that calculation, or obviously how to use tables to figure out the rate law, the orders, the rate constant. We did a variety of different sort of examples here. Any questions on any of that there? Okay, so we'll lay it up there for lecture, and we'll have lab at 11:30. Again, make sure you come through the lab link, and we'll be doing some stuff there, maybe some safety stuff, and maybe some more